All right. Thanks everybody for coming to our very first seminar of 2026. It's been a little while since I've seen all you, so thank you very much for coming. My name is Cinnamon Moffett. I'm the Associate Director of Marine Research Support here at Hatfield. If you haven't been to one of these in a little while, or you might be new to us, this is a hybrid event. So we have folks online and folks in the room. For folks online, if you have any questions, go ahead and put them into the chat box. Your cameras and mics have been disabled for today's event, but we have a volunteer, Roseanne, in the room who's going to help us navigate any of those questions, so feel free to communicate with us. For folks in the room, once we get to questions and answers, just raise your hand and I'll bring you this mic so folks online can hear your questions as well. And I just kindly remind you to sign in as you come in, or if you didn't, sign as you go out. That helps me justify buying cookies and coffees for us all, so I appreciate that. And that way I don't get in trouble for buying them for myself. Okay, so I wanted to do a couple of quick reminders. First of all, I just wanted to let everybody know, if you haven't already, Big Blue Film Fest is next weekend. So if you haven't bought your tickets, there's still a couple left. So that is a festival on Friday and Saturday here and at the PAC. That's all different marine themed movies. It's a pretty cool event. And we've got a lot of the producers and creators of those episodes coming to speak with us from all over the world. So that's going to be a pretty good one. So I just want to remind you of getting your tickets. I also have a request. I have an unexpected opening on seminars for February 12th. So if you know anybody who would like to give a talk, come talk to me. If you would like to give a talk, if you have a canned talk in a pocket somewhere, come see me. Have a gap on February 12th. And then for next week's seminar, which will be the 22nd, we have Eric Velasquez. I'm going to say his name completely wrong. He was a postdoctoral scholar from the School of Civil and Construction Engineering at Oregon State University. And he's going to come and talk to us about an update to the Newport tsunami hydrological models that include scour. And so what that means is that we're all familiar with the green, yellow, and orange maps that show inundation that were produced many years ago. We now have the computing power to add other variables to those. So we've added sediment transport and some of those things, and it's changing the models. And so I saw his presentation and invited him to come talk to us. So I'm excited to see that. So come join us next week. But the reason we're all here today is to hear Hannah speak to us. Hannah Glover is a research associate at Oregon State University. She received her BA in Earth and Oceanographic Sciences from Bowdoin College in 2013 and worked with UW's Applied Physics Lab until 2016. She completed her PhD in oceanography at the University of Washington. And then during her PhD, her research focused on coastal change following the Elwha River dam removal, sediment dynamics, and the AER Wadi, again, I'm going to mess that one up, River's mega delta in Miramar, and the impacts of mango removal in coastal New Zealand. And her current work at OSU focuses on expanding applications for distributed fiber optic sensing and measuring nearshore processes in sediment transport. So we're building on the sediment transport idea here. So go ahead and turn on your mic and I'll hand this off to you, Hannah. Thank you for being here.
Great. Thank you so much. I'm excited to be here. And I've heard Eric give talks before. It's great. His work is super fascinating. 10 out of 10 would recommend. But here today, I'm going to be talking about different applications of fiber optic sensing in the ocean. And I'm hoping that this talk will appeal to a broad audience. I'm a coastal engineer slash geomorphologist slash oceanographer. And I know many people here are more biologically focused. So I tried to work in a bunch of different topics, and hopefully some of this grabs your attention and you'll start thinking about how this tool or technique can help with your own research. So I'll just start with a little inspiration for that thought. So this is a map of some, not even all, of the submarine fiber optic telecom cables that are carrying our internet currently. So this is what's connecting us to other continents, allowing us to rapidly communicate with other people around the globe. This is a really well-maintained and intense infrastructure that's all through our global oceans, including in locations that are really hard for us to access, like polar regions. And the basic question that we can ask ourselves is, what could we learn as oceanographers if we could use this array as a sensor network? And that's where distributed fiber optic sensing comes into play. So this is a whole field of measurement techniques. It's not a single technique, but all of the types of fiber optic sensing in this field operate on basically the same principle. And that's that you have an instrument called an interrogator that's attached to one end of a fiber optic cable. So it'd be plugged into at the shore station of a telecom cable. So on land, the interrogator sends out a pulse of light and looks at the backscatter from that light. And the backscatter is related to the environmental conditions on the cable. And you can get a measurement of what's happening every couple meters along that cable for kilometers. So it's a really powerful yet fairly simple technique. And today I'm really going to focus just on two types of fiber optic sensing. That's distributed acoustic sensing, or DAS, and distributed temperature sensing, or DTS. And I might slip into immediately using those acronyms. I'll try to stop myself from doing that. But I'll start with just a very brief background on DAS. Distributed acoustic sensing relies on Rayleigh scattering. So here on the left-hand side of the screen, we have a plot where the x-axis is the wavelength of the light that's being returned to the interrogator. And on the y-axis, we have signal intensity. So you'll see that the strongest peak is at whatever light frequency you're inputting into the cable. So the interrogator is sending out a pulse of light with a specific wavelength, and it's getting a lot of that light wavelength reflected back. That's Rayleigh scattering. And based on Rayleigh scattering, we can infer the strain on the cable and the temperature. We can do that for up to 150 kilometers at about a meter every meter along the cable at tens of kilohertz. So we can generate terabytes immediately. The other technique that I'll talk about today is distributed temperature sensing, which looks at Brillouin scattering. So instead of looking at the same wavelengths of light that you're inputting, you're looking at, there's a shift in wavelength that is strongly dependent on temperature. And so we can use, there's actually a lengthening and a shortening effect. And we can look at the ratio between those two signals and derive the temperature of the cable. And we can do that only for about 20 kilometers. Say only, that's still a long distance, every less than a meter, and at seconds to minutes intervals. And just to put that sort of in the context of measurements in oceanography, here's a Stommel diagram. If this is not your cup of tea, that's totally fine. I just wanted to show basically the same information from the last slide, but in a slightly different format, if this is a diagram that you're familiar with. So on the x-axis here, we have spatial scale, and it's a log scale from processes that are operating over centimeters to processes operating over tens of thousands of kilometers. And then on the y-axis, we have that same concept, but for time. So processes operating over milliseconds up to hundreds of years. And we have a lot of different oceanographic processes that we could study. This Stommel diagram is primarily focused on physical processes, but the pink bars on the outside of the graph are showing the spatial and temporal ranges that are covered by DAS and DTS. So this instrument can provide measurements of a huge range of processes simultaneously because we're sampling at really high spatial frequency over large distances, and we're sampling at really high temporal frequency for continuously as long as you want. So we can really cover a lot of these different processes from sounds in the ocean up to mesoscale or seasonal changes in circulation. So that's a whirlwind intro to distributed fiber optic sensing, and specifically DAS and DTS. Most of this talk, I actually just want to go through applications, different submarine applications of DAS, submarine applications of DTS, and then I'll give a little bit of background on a field experiment that we just finished in Rockaway, Oregon, using both DAS and DTS to understand coastal change and beach processes, which is really what I'm excited about. But I wanted to make this more of just a come and take a snack kind of talk, a charcuterie board. Hopefully there's some piece of it that's interesting to you. Ignore the rest. And that's how I'm framing this. So I'll start with submarine applications of distributed acoustic sensing. So just very brief recap, we have distributed acoustic sensing is a technique where the interrogator is measuring the phase shift in light from a reflected laser pulse. And that primarily today, I'm just going to talk about how DAS can be used to measure cable strain. I'm not going to get into as much how it's measuring temperature. But for the cable strain, that strain it's a change in cable length over some reference length, which is called the gauge length. And over that reference length, we have nanoscale sensitivity. So we can detect very, very fine vibrations on the cable over, even though we're measuring over a meter or a couple of meters. So we can generate measurements at meter scale resolution for tens to hundreds of kilometers, depending on the cable, and continuously at tens of kilohertz. And I'm going to sort of go through applications of DAS from highest frequency to lower frequency, starting with there have been some really cool new studies applying DAS to record whales. So it's hard to track whales. Frequently, people put out hydrophones in specific locations, knowing where those whales are going to transit. But there have been people asking the question basically like, could we be using our existing telecom network to also be monitoring whale behavior? So this is an example from a study near Svalbard, where there's actually two sub-parallel cables connecting the mainland to an island. And on the inner and outer cable, they recorded DAS strain data. And here on the bottom, I'm showing just an example from this paper where on the x-axis it's been cut off, but it's time on the x-axis, and then distance on the y-axis, and the color of the plot corresponds to the intensity of the signal being measured. And you'll see those strong chevrons, which are whale calls. Here they were recording fin whale calls. Very similar work has also been done on the Oregon coast, using our own cabled arrays out here. So this was work by William Wilcox group up at University of Washington, where they were recording very similarly, looking for acoustic signals in the water column. So here we have time on the x-axis on the left-hand side. And then instead of having distance on the y-axis, we're just looking at a single location, now considering the different frequency content that's being recorded at that single location. And what they were able to identify were these specific blue whale calls. I'm not a biologist, so I wouldn't be able to identify a blue whale call, but this paper is really cool. And in a similar vein, they can identify not just blue whales and actually track blue whale speed based on how those whales are transiting over the two cables. They can do the same thing for ship traffic. So they have AIS records of vessels. They went and looked to see if they could calculate transit times for vessels and see what kind of noise those vessels are generating in the ocean. And that's what we're showing here, where same sort of spectrogram, that noisy signal between like 40 to 60 hertz is that vessel passing right over the cable. So those are acoustic signals that have been recorded with DAS. But moving to a slightly lower frequency band, not even that much lower, there's also been a lot of applications of submarine DAS in the world of seismology. So seismologists want to be able to study geologic processes happening on the seafloor. There's all sorts of fascinating and potentially harmful to human processes happening on the seafloor, like our Cascadia fault system, that are really difficult to monitor and study. So it's, once again, often a matter of putting out individual instruments in a few locations. And so seismologists have been really excited at the applications of DAS for studying these processes in the ocean. So this is an example of a relatively early study, just from Ethan Williams in 2019. This was part of his PhD. They collected data on a cable off of Belgium. And on that cable, they showed just a snapshot of what overall they're seeing on the cable, which is looks like just noise to me, where in this middle panel, they have time on the x-axis and distance along the cable on the y-axis. And you're seeing a variety of signals at a variety of frequencies. There's all sorts of different physical processes being recorded. But if you look at just a single location and calculate the power spectral density and just look at specific frequencies, we can see that there are a variety of processes that are being simultaneously recorded on this cable. So they're interested in things like teleseism, so distant earthquakes, or secondary microseism, where they can use actually wave-wave interactions and how that minutely shakes the seafloor to look at the structure of the seafloor, all sorts of really fascinating things. But as an oceanographer, the piece that I'm most excited about from papers like this is that they're seeing this really, really strong signal associated with ocean surface waves. And so this kind of thing where seismologists were like, oh, we happen to see ocean waves. Should somebody look at that? Is what inspired our group to start using DAS for more physical oceanography. One of the first things that we wanted to do was sort of demonstrate proof of concept that we can use DAS to measure waves. And a great place to try out new technology is the Army Corps' Field Research Facility in Duck, North Carolina. This is an amazing facility. They do a lot of long-term monitoring, and they have a variety of instruments permanently deployed. And it's also a place where people test out a lot of new instruments, where you can really compare apples to apples against well-vetted instruments. So it's perfect for us. And in 2021, Megan went out and installed a fiber optic cable cross-shore from the dune all the way out to about 15 meters water depth using an amphibious vehicle. And then we collected DAS data for 3 months through the winter. And I'll give you an example of what that data looks like in the nearshore. So on the x-axis here, we have distance across shore, where the beach is this sort of low energy zone. We have time on the y-axis increasing. This is just 5 minutes of data from that 3-month deployment. And the color is the strain signal recorded on the cable. And you'll see that there are these really strong bands of compression in yellow and extension in blue. And what we're actually observing is a wave propagating onshore, passing over the cable and compressing it, and then shoaling as it approaches the shoreline and eventually breaking. So this sort of qualitative result was really exciting to us, that we can basically visualize waves and track a wave from offshore to onshore over its lifespan, basically. And we wanted to be able to quantitatively look at these waves and look at a variety of physical processes in the nearshore. So our next step was to go from working in strain units, which are not useful for an oceanographer, to working in units of pressure. So what is the pressure at the seafloor that would generate this strain signal? And we converted that empirically as a relatively fast, efficient first step. So we took one of the pressure sensors that is deployed out there, and we looked at the strain at the nearest channel. And here in these spectrograms, I've flipped them. So we have frequency on the x-axis and time over the month of November on the y-axis. And you'll see that they're recording remarkably similar frequency content, just in very different units. So we basically use the pressure sensor to empirically calibrate the strain. And then from that, we were able to accurately calculate a variety of wave parameters and statistics. So here I'm just showing example of significant wave height at the top and peak period at a single location at about 11-meter water depth. Where in black, we have 2 different ways to measure those things from traditional instruments. And then in red, we have the result from our calibrated channel of strain. You can see that they're pretty consistent, and that we were then able to use this in a really dense cross-shore array of pressure sensors to look at a variety of physical processes. This exact same technique was also applied in the Arctic, where it's really difficult to collect data as the sea ice extent is changing, but you really want to be able to understand the interactions between waves and circulation and ice formation or breakup, but your instruments tend to get destroyed in those types of environments. This is from a paper that Maddie Smith put out in 2023, where they collected data on the north slope of Alaska on a fiber optic cable there. And they were able to calculate wave height and period from that cable all across the shelf, and then use that to look at wave attenuation into the ice zone. And they're able to really accurately identify the edge of the ice. And even with higher spatial resolution than you can get from the most commonly used satellite product for that type of work. So they're getting really nice results in a very extreme environment. In addition to looking at wave processes, we also have physical oceanographers who are starting to think about other applications of DAS to measure, for example, turbulence in the ocean. So this is data that was collected in the UK, where they have a cable that's installed in a region with really strong tidal currents. So on the bottom here, this is just over one full tidal cycle. You'll see that there are periods of time where the flow speed is really, really low, and then it jumps up to a high speed and then drops back down again. That's just tides going back and forth. And they recorded DAS data through a bunch of tidal cycles and really looked at how the strength of the currents generated signals that could be recorded as vibrations on the cable. So on the top here, we have time on the x-axis, frequency on the y-axis, normal spectrogram, where the yellow colors are more intense energy recorded in that frequency band. And you'll see that there's a lot of vibration generated on the cable during those high-speed currents, and they're actually able to develop a relationship, a quantitative relationship between that sort of vibration and the turbulence, and then say something about the turbulence generated in this narrow passage by strong currents. That was a bunch of different applications of distributed acoustic sensing. Oops, some of them were interesting. I'm going to do the same thing with submarine applications of distributed temperature sensing. So just a very brief reminder, for distributed temperature sensing, we're looking at the ratio of two different scatterers that are strongly affected by temperature. I guess one is not strongly affected by temperature and the other is, so they're really useful as a ratio. And from this calibrated ratio, we can measure temperature over some reference length, usually about a half a meter to a meter, with 0.01 degree Kelvin or Celsius sensitivity for tens of kilometers and at pretty high frequency. In general, with DTS studies, they're not looking at changes in temperature that are happening over seconds, so usually the measurements are recorded over minute intervals. And I just want to re-emphasize that with DTS, one of the challenges, but also one of the really fascinating pieces, is that the calibration is key. So the instrument itself is not really putting out a meaningful environmental signal. It's giving you the ratio of two signals. And a key part of deploying any DTS system is basically running portions of your fiber optic cable through reference baths where you're controlling the temperature, and then using those controlled segments of the cable to develop a specific calibration for that cable type and environment. And then you can use that calibration to get a really high fidelity measurement of temperature all along the cable. So this is an example of a setup that we did in a hotel room. It's a fridge that we ran some fiber optic cable through so we could control the temperature. And we had reference measurements, which on these two example plots are shown as black dashed lines, and then the DTS for the nearest channel, where once it's calibrated, we're getting a really good match in temperature between the reference and the cable. that's enough of the nitty-gritty background. Let's go into a few applications. So DTS has also been used in the world of physical oceanography, primarily to look at internal waves and how those propagate up onto the continental shelves. So this is an example from a paper by Kristen Davis, where they collected data off the coast of China. And I love this like 3D view that they put in the paper. So on the y-axis, they have depth through the water column. On the x-axis, they have distance from the reef. That was sort of their reference point. And then on the other x-axis, they have time. And the color of that sloped bathymetry is the temperature that was recorded on the cable at that moment in time. And you'll see these sorts of, well, maybe my mouse won't show up. That's okay. Pointer. You'll see these internal waves that generate a change in the temperature signal, and we can see those waves propagating onto the shelf and then relaxing back. And I'm not a physical oceanographer per se, I don't look at internal waves, but there's all sorts of fascinating information you can learn about the speed that the wave is traveling and where it was generated and all sorts of things like that. Very similarly, there's another study, this time at the Martha's Vineyard Cable Observatory off the coast of Massachusetts, where they actually deployed a cable parallel to shore. So instead of a cross-shore cable, they had one parallel. And on that cable, they were also able to observe internal waves that generated a temperature signal that propagated up onto the cable. So those are two examples of where we have a fiber optic cable laying on the seafloor. We're able to look at how temperature is evolving and how that relates to physical forcings. But there's nothing that requires your cable to stay on the seafloor. You can also use your cable as a vertical array. And this is actually really common in terrestrial applications, where a fiber optic cable will be tethered to a weather balloon, and DTS data will be collected up through the atmosphere or through a cave system where they want to know the air temperature and how that's varying. So those same folks who think a lot about terrestrial applications basically were like, let's do that in the ocean. So this is a great example of a study that was done on the Ross ice shelf in Antarctica, where they really want to understand what's happening underneath the ice shelf, but that's obviously very difficult to access and to monitor over long time periods. And so what they did was they drilled a hole and they ran a cable from the DTS system that was anchored on the ice shelf. They ran a cable down through the hole and all the way down through the water column. And what they were able to collect was about 6 months worth of data. So December through June, over 500 meters of the water column, they're able to measure temperature continuously using this one instrument. And the instrument itself, the expensive bit, wasn't even in the water. And from this, they can learn all sorts of things about ablation and melting and circulation underneath an ice shelf. So all of those sort of are more in the realm of physical oceanography. As a more geomorphologist, I was interested in how we can use DTS to look at changes in the seafloor itself. And there are all sorts of fascinating terrestrial applications or riverine applications of DTS where people have demonstrated that they can actually measure the depth that the cable is buried at in sediment or in gravel based on the difference between the water temperature and the cable temperature. So whether or not the cable is being insulated from changes in the water temperature. And we wanted to see if we could do that same thing for a cable in the ocean. So going back to our field research facility data set, we didn't just collect DAS data, we also collected DTS data. And this is just an example of what some of that DTS data looked like, where once again, we have the cross-shore distance on the x-axis where the beach is to the left here. And this now I'm showing about 2 days worth of data. And the color here is the temperature. So most of the variability in the temperature is happening here in the beach, where the cable is alternately is underwater and strongly controlled by water temperature, or is in a dry portion of the beach and is more, the temperature is controlled by incident sunlight or air temperature. But there are also changes in the temperature of the cable offshore, where we would expect relatively uniform water temperature. And if we look just at two examples, so two locations along the cable, one that's on a section of the cable that had been buried underneath a sandbar that had migrated a little bit onshore, and then a segment of cable that was not under the sandbar, we see a strong difference in the temperature of the cable. So on the buried segment of the cable, that's that purple line. We have a relatively constant temperature slowly changing as the water temperature slowly changes. But on the unburied section of the cable, we're seeing a lot more variability in the cable temperature. It's responding to smaller changes in water temperature because it's directly exposed to that water. And so we're still in the process of developing the best model to convert from this relative variability in temperature to actual cable burial depth. But that's something that I'm really excited about, is being able to use a fiber optic cable to actually track sandbar migration or bed form migration on the seafloor. So with my last 10, 15 minutes, I just want to cover a recent experiment that we did in Rockaway, where we collected both DAS and DTS data. I don't think that I need to hammer home motivation to this crowd, but I'll just put in a plug that coastal erosion is a problem, especially on sandy beaches. It causes all sorts of damage to infrastructure, livelihood, human access to beaches. And it's really important to be able to understand how sand moves and migrates in response to wave motion in order to predict where and how coastal erosion is going to happen. And there are all sorts of really small scale and very specific processes that are happening in the beach as the waves are interacting with the sand and the sediment. And one of the processes that's happening that we know is happening on a local vertical scale is these vertical pressure gradients that can change how easy it is for sediment to be resuspended under a wave. So when we're in shallow water, we have the crest of the wave, the trough, and then the crest passing over the same location on the beach. And under the trough, we have a slight de-weighting of the sand that, depending on the type of wave that's passing over the beach, can actually be enough to generate momentary liquefaction, which is where we have those sand grains losing contact with each other and losing all their structural stability, which makes it really easy for that sand to then be remobilized and transported elsewhere. So we know this is happening sort of on a local scale. There are these like really complex vertical processes happening on a wave by wave basis, so over the matter of seconds or less than seconds. But we don't have as good a picture of how that's varying across the shore. And the real challenge is that we need to be able to measure these processes that are happening wave by wave with a bunch of pressure sensors that are all time synced and linked to each other. And that's really where the like fiber optic sensing light bulb went off. We're like, this is the perfect tool to really address this challenging and methodological and research question. So right now I'm funded on an NSF project to specifically look at how these pressure gradients vary across shore and how that's related to net sediment transport. But a second piece of this project is really to push the boundaries of distributed fiber optic sensing, so develop new techniques for coastal oceanography that are built on this really awesome technology. And a big piece of this grant was collecting field data. So we were looking for a location where we could install a cable cross shore in the beach and have our instrument be safely housed inside of a building. I contacted a bunch of local hotels with beachfront access. Rockaway Beach Resort answered really positively. They were amazing to work with. We're really excited to engage with the scientific community. And so we rented a room there and set up all of our instruments and collected data for a month this fall. And did So our goal was to collect both use traditional sensors such as RBR duos to measure both pressure and temperature, as well as collect DAS and DTS data on a cross-shore cable. So our first step, once we found a hotel, was to actually install a cable. We have a spool with about 1.5 kilometers of fiber optic cable suitable for installation in a beach. So we backed a truck up to the beach, unspooled a bunch of cable, and dug a 30-centimeter deep trench across the beach with all permissions, etc., all the paperwork. It took us about a full tidal cycle. We basically chased the tide out, installing that cable. We installed a layer of cable at 30 centimeters, partially filled in our trench, and laid another cable at 15 centimeters. So we actually have two vertically stacked cables that we can use to look at vertical and horizontal pressure gradients in the beach. I slightly miscalculated in off-spooling all of that fiber, so we actually have a little bit of extra fiber that you'll see loops back onshore here, so we just have like even more data, which is fine. And every 30 meters or so along the cable, we attached a RBR pressure temperature combo sensor as a ground truth. So this sort of array here are just all the pressure sensors sort of offset, so you can see that they're each recording signals. And this is the sort of traditional data array that you might get with like, if you just were to put out 8 pressure sensors. So you'd have 30-meter spatial resolution. But with DAS, we were able to get a lot better than that. So this is the hotel room that we lived out of. I just lived with my instruments for a month. We collected DAS data with 3.19 meter spacing, so that's about 200 sample locations in the beach. We're recording at 2 kilohertz. And then we collected DTS data with about 25 centimeter channel spacing or measurement spacing, so that was 1,000 measurement locations in the beach. And we were only recording every 10 minutes because we weren't looking at those really high frequency temperature signals. And that was about 5 terabytes worth of data, which in our world at this point, in the world of DAS, feels like such a manageable amount. We deployed this in the fall, hoping to get some good storms, and we got some great storms. Got a lot of really great data, some really large wave events that were recorded with our instruments. Over that time period, we're collecting regular beach surveys to ground truth how the beach was changing. And because we had some big storm events, we also had significant change to the beach profile, which is really helpful for our experiment, where we're really trying to see how many of those signals we can identify in the DAS data. So these are profiles of the beach just collected along the path of where the cable was laid. The darker blues are earlier in the deployment. So early in the deployment, we had this nice beach cusp on the upper beach, and then sort of a smooth profile down to as far out as we could get at the lowest tides. And over the course of the month, that cusp was completely reworked, and sediment was deposited on the upper beach face and eroded from the lower beach face. So I don't think we had a significant change in the total amount of sediment on the beach, but we had a significant change in the profile. We were of a really steep beach by the end. And I'll just give you an idea of what the DAS data looks like. Very similar to what we were seeing in the duck, so the field research facility data that I was showing earlier, but now our x-axis is flipped because we're on the west coast. So the shoreline is here on the left, and then offshore is over on this side. Once again, time increasing up the y-axis. And this is only about 5 minutes of data, where we're really seeing, once again, those individual waves propagating onshore. And then actually we're seeing some of the run-up is that sort of like faint signal that you can almost not see in the beach. Really, once again, we want to go from a qualitative perspective to a quantitative perspective. And that's where instead of going down the empirical route, we've actually been doing a lot of work in the lab, trying to develop an analytical transfer function between recorded cable strain and the pressure that is required to generate that strain. So incorporating all of the factors that influence how the cable is responding to the ocean. And I'm not going to go into all the boring details on that. That's like a whole nother seminar. But basically we can, I'll just show you briefly that we're doing pretty well with it, which is exciting. So I'll just show one brief validation from a channel of DAS data in a single RBR pressure sensor location, where in blue, on all of these plots, we have the DAS data, and in black, we have the ground truth RBR data. On the upper panel here, I'm showing 45 minutes of data. We are seeing a lot of waves, and it's just really noisy, but overall, it seems like the magnitude of the pressure that we recorded is very similar to the analytically derived pressure that we get from the DAS. If we zoom in on just 1 minute of data from this 45-minute record, you can see that there is a difference in exactly what these two sensors are recording. Part of that is because they're not perfectly located in space together. But part of it is that they're sort of fundamentally measuring slightly different things, and we're still working out the details of that. But if we look at this in sort of like what energy, what frequencies are dominantly being recorded by the pressure sensor and by the cable, so looking in frequency space, we see that there's a strong peak at exactly the same frequency, and much of the same frequency content is recorded by both of these instruments. So that's all still a work in progress, and same for this next piece, which is that we're still trying to develop ways to use the distributed temperature sensing to monitor bed change. So here's temperature recorded over our full experiment. Once again, the beach, the hotel sort of is over here, offshore is on this side. And you'll see that the temperature is, there's both cross-shore variability, but also variability in time. And especially there are times when it seems like the signal magnitude on the cable is really changing. And we can look at how that variability is related to changes both in the environmental conditions, so the air temperature, but also due to changes in how deeply the cable was buried under that cusp, or how sand was being reworked over the surface of the cable. And we're going to be doing that by comparing the cable temperature to our air temperature signal and looking at how the variability in those two signals changes over the course of the experiment. So all of that's just to get back at these two big research questions. Well, one is more of a science question of the relationship between those cross-shore pressure gradients and net sediment transport. And then the second one of improving our methods for distributed fiber optic sensing as it relates to coastal oceanography. With that, I'll just wrap up with sort of the big picture takeaways, coming back to our Stommel diagram, that DAS and DTS are really versatile, and there are so many applications for both of this technology. And the thing that I find most exciting is that there are applications for a single data set that could be related to all of these different fields in oceanography. So you could collect one data set and have a really interdisciplinary team look at it, at how all of those signals are related to each other. And that at the same time, you're collecting data at unprecedentedly high spatial and temporal resolution. And so you can get a really detailed picture of the environment just using a fiber optic cable and an instrument onshore. And if any of that's interesting to you, I strongly encourage you to check out the Center for Transformative Environmental Monitoring Programs, CTEMPS. So CTEMPS is a multi-institution organization at OSU, University of Nevada, Reno, and Colorado School of Mines, which I forgot to put up there. They provide instrument rentals, so they provide DAS and DTS instruments along with all of the paraphernalia, but they also provide a lot of training, both in the form of online videos and tutorials, but also really intensive like week-long workshops or day workshops, often associated with a conference. So if you're interested in getting trained up on this so you can deploy an instrument for your own research, they're a great resource, and I'm happy to talk more about sea temps. The other thing I want to advertise is just that we now have an array of fiber optic cables just off the coast. So the PacWave South array is up. There are 4 about parallel fiber optic cables on the seafloor. And Megan and I have been talking a lot about like what sort of interdisciplinary data could we be collecting on those PacWave cables using DAS and DTS? What questions could we answer about our own coastline? And if you're interested in any of that, please do come and talk to one of us. With that, I'll say thank you. And I'm happy to take questions.
That was really cool stuff. A lot of that I didn't know yet, so that was very cool. Okay, so we're gonna go back and forth, and I can already see we've got a question online, so go ahead, Roseanne.
It looks like a significant amount of sand moved on the beach. How close did it come to unburying your cable, and how worried were you?
That's a great question. I was very worried about cable burial. I was out there every day looking for my cable to see if it was exposed. The cable that we were using has a fair amount of metal protection inside of it, and it's intentionally weighted to have a greater density than the sand in water matrix. So it's designed basically to self-bury in the sand. So we were not seeing the cable being exposed because as the sand was moving, the cable was basically sinking itself to the same elevation. So what we were observing was that the cable was basically maintaining the same depth in the sand, even as the beach profile was changing, which was convenient. Except in places where we had additional deposition, and then the cable wasn't like working itself back up to the surface. So we'll have a lot of really interesting signals to look at from the perspective of calculating cable burial.
Questions in the room?
A very nice talk. I'm a biologist, so this is all rather new to me. But one of the things that I was puzzling over, I can understand how a cable can respond to a particular signal in one location in one instant of time. Can you, without bamboozling us too much with mathematics, explain how it can respond to multiple signals on the cable at different locations?
Yes. So I think I'm actually going to pull that into a little bit of 2 different pieces. So the cable itself, you could imagine if we had a cable laid here on the floor, if it was a really soft cable, I could step on it here and squish it, and that part of the cable over there maybe would not respond very much. So that's sort of the piece of like one section of the cable can be strongly impacted by, like if I pointed a heat gun at this section, it would warm up, and the section over there would not. So we can have strong variability in the cable itself. The physics behind how fiber optic sensing is able to provide a measurement every meter or so along the cable is basically related to the speed of light in glass. So the instrument knows when it sends out the laser pulse and it records when that laser pulse comes back, and it calculates basically like where those scattering signals are coming from based on how long it took those scatterers to come back to the instrument. So it can say that scatterer there must have been like 5 kilometers away. And if we're measuring strain, it can say that scatterer that I was just looking at was 5 kilometers and 1 millimeter away last time. And now it's 5 kilometers and exactly 5 kilometers away. And so that little like 1 millimeter of change in how far away that scatterer was is giving you is telling you that the cable at that segment has been compressed or extended. Not a great, that's actually like a vast simplification, but I don't want to get into the details of how exactly it works, but it's basically speed of light.
Can I build on that real quick and just ask, so you step on the cable in your example.
Yeah.
How do you also have another signal happening at the exact same time? and be able to read both of those. So in your examples, you were talking about a surface wave versus a internal wave. How do you see both of those in the exact same place at the exact same time?
For signals that are happening at the same place, what we're generally looking at, I'm actually going to go way back. I think a picture is very helpful here. This figure from, I love this figure from Ethan Williams. So over here, this is all data that was recorded at a single location on the cable, but we see different frequencies. So if I'm tapping my foot every 1 second, you'd be able to tell the difference between that and the fact that the cable is recording my voice, which is a signal at a much higher frequency. So mostly we use frequency and wave number differences to separate out environmental signals.
Awesome talk.
Thanks.
Fascinating stuff. I think that the situation is analogous to an acoustic echo sounder on a boat.
Yes.
That's just timing the returns. How is it not analogous to an echo sounder in the sense that does it not integrate, like the 1 kilometer away signal, does it not integrate all of the effects on the cable between, 1 to 999 meters and isolate the process that's happening at 1 kilometer?
Yeah.
Is it just because speed of light and glass is the speed of light and glass, period, and you don't care what it's passing through? Or
No, I'm hoping, I guess this ignore all the text. So the nice thing about fiber optic sensing is that it is not integrating all the signals over that distance. So that is a difference from an echo sounder. So DAS specifically in general is basically comparing 2 adjacent segments of the cable and saying how have the scatterers in those 2 adjacent segments shifted relative to each other. And that's where we get into the fact that the strain or the temperature is fundamentally measured over some reference length. So the instrument needs a reference length where it can compare what's happening at this end of the reference length to what's happening at the other end. And that difference is really what's driving the signal that's output. So then you don't have to worry about what's happening anywhere between your gauge length and your interrogator. That makes sense?
yeah, that's cool.
Okay.
Would that also be the answer to why you can do this on different physical cables, different quality of cables, different types of cables, that it's not really dependent on the propagation characteristics of a good cable or a bad cable so much?
So all of the cables basically have a very similar glass. So when I talk about different cables, I'm really talking about all of the stuff that's going around the glass. The actual glass is about the size of a human hair. And everything else is preventing that glass from being eaten by a shark or whatever. There's a recent New York Times article about that happening to telecom cables. And so that glass has very specific properties and is manufactured to have a very specifically known speed of light. It's also manufactured to have a very specific diameter, which controls the type of signal that can be sent down it. So one of the things I didn't get into is that DAS and DTS actually use slightly different diameter of fiber optic cable. And so not every cable on the seafloor, so all the cables on the seafloor have a bunch of different fibers of glass. So there's not really a point in putting out this heavy duty metal cable with one single thread of glass. They put out cables that have a bunch of different fibers. In general, they're all diameter known as single mode. Sometimes cables will have multi-mode fiber as well. DAS operates on single mode, which is really common. It makes it really easy to use DAS on any telecom cable in the world. DTS requires multi-mode. It's also why it only operates over a shorter distance, and multi-mode glass is not as common. feel like I've lost track of your original question. Sorry, Scott.
No, but you addressed the question about
Yeah.
like that it's a fairly universally applicable
Yes.
process because of the constancy of that glass.
Yes, exactly.
Thank you.
So on sorry, everybody, I have questions. I think it was on slide 15, maybe, you started to show the noise based on distance from the interrogator, maybe?
This 15.
Maybe it doesn't matter the slide. Nope, no, that's not the one. Okay, so talk to me a little bit about how you know when the return is not accurate anymore, and where that line is that you're starting to see more noise than.
Yes. So DAS, so the point at which the signal is no longer useful has to do with basically how much light is being scattered. So you're sending out a laser pulse that's very strong. Immediately, that laser pulse is being attenuated by scattering in the glass just due to natural impurities. And at some point around 150 to 200 kilometers, your signal is weak. And that's the point at which you can no longer rely on those backscatters to give you a good signal.
And that's a known point.
Yes. Yeah, it's something you can measure. So it'll vary a little bit depending on exactly the glass properties, but and exactly your instrument. The bigger problem for us is that telecom companies, they know this. They are routinely sending light across the ocean. The way they do that is that every 50 kilometers, they put in what basically an amplifier that takes in the signal, boosts it back up, and sends it back out. The instruments that we own cannot operate through one of those systems. There are instruments that are currently being developed and are like just now, like this year, entering the market that can operate over the entire span of the ocean by passing through one of those repeaters. But that's not the one we have. So theoretically, our system can operate over about 200 kilometers. Functionally, if you're working specifically with a telecom cable, it's 50 kilometers. But there are all sorts of applications where you could put out your own cable that is longer than that.
Other questions in the room?
Yeah, thank you very much. Love the talk. So I love these passive acoustic uses, but I was wondering if there has been much use on more of an active acoustic sense.
Yeah.
And if you're involved in any of that kind of research.
I have not been. One of the leaders in the field of using DAS for active acoustics is Zach Spica, who's a seismologist and geologist. So most of the applications have been very much directed at using DAS to understand the layers of the seafloor. And I could have included an example. I don't know why I didn't. Of that sort of application, but very like geology focused. I don't know of as many active acoustic studies using fiber optic cables that are related to other applications. I know it's a huge field.
Great. Any other questions? Oh, Joe, of course. Hang on, everybody. I got to walk to the top of the auditorium.
Thanks. My question may have already been answered by some of the discussion we've been having, but I was curious about the reference for the DTS. And so does that always need to be in place? And if not, or if so, is it because there's drift that could happen?
Yes. So there's 3 different parameters that go into the calibration. So you need 3 reference locations to solve the system of equations. One of those parameters is just related to the cable composition, so that's constant and would not need to be monitored. So like if you know your cable well and have deployed it in other locations, you could get a really good fix on that variable. The second one is related to how light is attenuating down the cable, which can be impacted by bends in the cable and by any connectors that you use. So that would be very situationally specific, where you'd really need to derive it for your specific application. I'm forgetting what the third variable is related to. But in general, it's considered best practice to always have references. Those references can take a lot of different forms. So we had a lot of basically like natural reference points where we were measuring the temperature in the field along the cable. So we had just 2 reference baths where we were controlling the actual temperature of the cable. But there are really small setups that people do in terrestrial applications where they basically just like have 2 igloo coolers next to each other to be able to get good references. There are people at CTEMS who would be able to answer your question about whether you could truly deploy without any references. But I honestly can't remember.
Well, it was really just for that like 1 month that you were up
Yeah.
the coast. Did you have to have that running for a constant month, or could you have set that up for the first couple days and then said that was good reference from there on?
Yeah, we wanted to have a continuous record in case our cable bends changed at all, which would have impacted our calibration. But yeah, I think I could play around with like only using the first day of data, and theoretically that would have been fine, and I didn't need to live with a giant fridge right next to my bed. Yeah, that's a great question.
Nice. Well, it seems like Hannah is interested in collaboration. And so
Yeah.
if anybody is interested, please reach out. And let's give one more round of applause for that really fascinating talk.
Thank you.
Thank you so much. And for everybody, hope to see you next week. Thanks, everybody.